They called it a flying coffin, a $35 billion boondoggle, an aircraft so dangerous that senators demanded its cancellation. Between 1991 and 2000, 4 developmental crashes killed 30 people, and critics said that the V-22 Osprey would never work. The program should have died a dozen times. Today, the Osprey is irreplaceable. Over 475 aircraft have been delivered. They've accumulated over 600,000 flight hours in some of the world's most demanding combat environments. From special operations deep in enemy territory to humanitarian missions in disaster zones, the V-22 has proven that revolutionary technology requires revolutionary persistence. Welcome back to Project Aerospace. Today, we're examining one of aviation's most controversial redemption stories, the V-22 Osprey. This isn't just about an aircraft that overcame technical challenges. It's about how a program survived political attacks, public scrutiny, tragic accidents, and fundamental questions about whether tiltrotor technology could ever be safe. The V-22's journey from disaster to dominance reveals critical lessons about revolutionary technology, organizational culture, and the difference between acceptable risk and reckless disregard. By the end of this video, you'll understand why the Osprey almost failed, how it ultimately succeeded, and why recent accidents have reopened debates that many thought were settled. If you're here for deep dives into aviation's most complex and controversial stories, hit that subscribe button and notification bell. Today's analysis goes beyond the headlines to reveal the complete story of the world's only operational tiltrotor aircraft. The V-22 Osprey's story began in the early 1980s with a simple but audacious question. What if we could build an aircraft that combines a helicopter's vertical takeoff with an airplane's speed and range? The Department of Defense launched the Joint Service Vertical Takeoff and Landing Experimental Program, JVX, in 1981. The requirements were unprecedented: vertical takeoff and landing like a helicopter, but a cruise speed of over 250 knots and combat radius exceeding 200 nautical miles. No existing aircraft could meet these specifications. Bell Helicopter and Boeing partnered to develop a radical solution, the tiltrotor. 2 massive 38-diameter rotors mounted on a nacelles that could rotate 90 degrees. In helicopter mode, the rotors pointed upward for vertical flight. In airplane mode, they rotated forward, turning the Osprey into a turboprop aircraft capable of 275 knots. The engineering challenges were staggering. The aircraft had to remain controllable during transition between helicopter and airplane modes, a regime where aerodynamics behave unpredictably. The rotors needed to generate enormous thrust for vertical flight while remaining efficient for horizontal cruise. And everything had to be reliable enough for combat operations. On March 19, 1989, the first V-22 prototype lifted off in helicopter mode, hovered, then slowly transitioned to airplane mode and accelerated into forward flight. It was a triumph of engineering, proof that tiltrotor technology could work. Military planners were ecstatic. The Osprey promised to revolutionize amphibious assault, special operations, and combat search and rescue. Marines could launch from ships far offshore, beyond enemy missile range, yet still reach objectives hundreds of miles inland. Special operations forces could conduct missions previously impossible due to range limitations. The V-22 wasn't just another aircraft. It was supposed to change how wars were fought. But within 2 years, that promise would be written in blood. June 11, 1991, during a low-altitude demonstration flight, the V-22 prototype number 4 experienced uncommanded pitch oscillations and crashed, killing both crew members. It was the first fatal Osprey accident, but tragically, it would not be the last. The 1991 crash was attributed to wiring problems in the flight control system, but it exposed a deeper issue. The V-22's fly-by-wire controls were extraordinarily complex and potentially vulnerable to cascading failures. Critics began asking whether tiltrotor technology was inherently dangerous. July 20, 1992, another prototype crashed during a test flight, killing 7 people including 3 Marines who were testing the aircraft's operational capabilities. The accident was blamed on flight control software errors, further evidence that the Osprey systems weren't ready for operational service. The program survived these early crashes barely. Defense Secretary Dick Cheney tried to cancel the V-22 in 1989, calling it unnecessarily expensive and technically immature. Congress overruled him, insisting the Marines needed the Osprey's capabilities. But public confidence was shaken, and every subsequent accident would bring new cancellation attempts. Then came April 8, 2000, the worst disaster in V-22 history. During a night training operation at Marana, Arizona, an MV-22 carrying 19 Marines entered vortex ring state during an overly aggressive descent. The pilot lost control and the aircraft crashed, killing everyone aboard. Vortex ring state is a dangerous aerodynamic condition where an aircraft descends into its own rotor downwash, causing a catastrophic loss of lift. It can affect any helicopter, but the V-22's high disk loading made it particularly susceptible. The Marana crash suggested that operational pilots didn't fully understand the Osprey's flight envelope limitations. Just 7 months later, on December 11, 2000, another MV-22 crashed in North Carolina, killing 4 Marines. This accident was even more damning. Investigators discovered that maintenance shortcuts and falsified records had allowed a hydraulic system failure to go undetected. The December 2000 crash exposed systemic problems beyond just aircraft design. There was pressure to meet deployment schedules, maintenance was rushed, and safety concerns were being suppressed. A subsequent investigation revealed that program officials had manipulated maintenance data to make the Osprey appear more reliable than it actually was. The V-22 program was grounded indefinitely. 4 crashes during developmental flight tests had killed 30 people. Congress launched investigations. Families of the dead demanded accountability. Defense experts questioned whether tiltrotor technology could ever be safe enough for routine military operations. The Osprey program faced its darkest hour. The aircraft that was supposed to revolutionize military aviation had become synonymous with failure, death, and Pentagon mismanagement. Many believed the V-22 was finished, that it would become another cautionary tale of overambitious military procurement. They were wrong. The grounding after the 2000 crashes forced a fundamental rethinking of the entire V-22 program. This wasn't just about fixing specific problems. It was about rebuilding the aircraft systems and the culture surrounding its development from the ground up. Engineers conducted exhaustive analysis of every crash, every incident, every near miss. They redesigned flight control software to provide better pilot feedback during transition. They improved hydraulic system redundancy. They developed new training protocols that emphasized the Osprey's unique flight characteristics and limitations. The vortex ring state problem that caused the Marana disaster was addressed through multiple approaches. First, engineers installed warning systems that alerted pilots when descent rates approached dangerous levels. Second, they developed simulator training that taught pilots to recognize and avoid vortex ring state conditions. Third, they established operational procedures that kept descent rates within safe parameters. But perhaps the most important change was cultural. The program established independent safety oversight with direct access to senior leadership. Maintenance personnel could report problems without fear of retaliation. Schedule pressure could no longer override safety concerns. The entire organizational structure was reformed to prevent a culture of normalized deviance that had enabled the 2000 crashes. In 2005, after years of redesign and testing, the Marine Corps declared initial operational capability. The first operational MV-22 squadron deployed to Iraq in 2007, a moment of truth for an aircraft that many had written off as unflyable. The Iraq deployment was carefully monitored. Every flight was analyzed. Every maintenance issue was tracked. Critics predicted disasters, but the Osprey performed remarkably well. The aircraft's speed allowed Marines to launch from bases far from the combat zone while still reaching objectives faster than helicopters could. The aircraft's speed allowed Marines to launch from bases far from the combat zone while still reaching objectives faster than helicopters could. The extended range meant fewer dangerous refueling stops. By 2009, Ospreys had accumulated over 100,000 flight hours in combat operations without a single fatality. The aircraft that had been called a widowmaker was proving itself in the world's most demanding operational environment. The transformation was remarkable. Departure reliability rates climbed to above 90%, mission-capable rates exceeded those of the CH-46 helicopters the Osprey was replacing, and most importantly, the aircraft was bringing Marines home safely after completing missions that could have been impossible with conventional helicopters. The V-22's redemption arc seemed complete, but the story was far from over. Since becoming operational in 2007, the V-22 has fundamentally changed how the U.S. military conducts operations worldwide. More than 475 V-22s have been delivered across Marine Corps, Air Force Special Operations, and Navy variants, accumulating over 600,000 flight hours in every operational environment imaginable. Now let's talk about what makes the Osprey operationally dominant. The aircraft can carry 24 combat-equipped troops or 20,000 pounds of internal cargo at cruise speeds of 275 knots, nearly twice as fast as any conventional helicopters. Combat radius exceeds 500 nautical miles with vertical landing capability, more than triple what CH-46 helicopters could achieve. These capabilities aren't just impressive statistics, they enable entirely new operational concepts. Marines launching from amphibious assault ships can reach objectives 300 miles inland in less than 2 hours. Special operations forces can infiltrate, conduct missions, and extract before dawn, all under a single cover of darkness. The CV-22 variant operated by Air Force Special Operations Command has proven particularly valuable. With additional fuel tanks, defensive systems, and advanced avionics, CV-22s conduct long-range infiltration and exfiltration missions that would be impossible for helicopters and too risky for fixed-wing aircraft. In 2011, V-22s participated in Operation Odyssey Dawn over Libya, conducted combat search and rescue missions and personnel recovery operations. The aircraft's ability to self-deploy across the Atlantic, flying over 2,000 miles with aerial refueling, demonstrated strategic mobility that no helicopter could match. Humanitarian missions have also showcased the Osprey's unique capabilities. When Typhoon Haiyan devastated the Philippines in 2013, MV-22s delivered critical supplies to areas inaccessible to fixed-wing aircraft and too distant for helicopters operating from ships offshore. The V-22 has supported earthquake relief in Haiti, tsunami response in Japan, and wildfire evacuation operations in California. The aircraft's combination of vertical landing capability and long range makes it ideal for disaster response where infrastructure is damaged and time is critical. Perhaps most remarkably, the Osprey has become the preferred aircraft for transporting the President of the United States during his overseas visits. Marine One operations now routinely include MV-22s in the Presidential Helicopter Squadron, a stunning endorsement for an aircraft once considered too dangerous for operational use. The V-22's operational success seemed to vindicate all the time, money, and effort invested in making tiltrotor technology work. But recent events have reminded everyone that revolutionary technology always carries risk. Since becoming operational in 2007, 12 crashes and several incidents have killed a total of 32 people. While the overall safety record has improved dramatically from the development years, recent accidents have reopened questions about the V-22's fundamental safety. In March 2022, 4 Marines died when an MV-22 crashed during a training exercise in Norway. In June 2022, 5 more Marines were killed in another training accident in California. Then in August 2022, 3 Marines died in yet another crash during exercises in Norway. The most serious recent accident occurred on November 29, 2023, when a CV-22 crashed off the coast of Japan, killing 8 Air Force Special Operations airmen. Investigation revealed that a pinion gear in a probe-rotor gearbox had shattered into 5 large pieces, causing catastrophic mechanical failure. The gearbox failure was traced to defective steel from the manufacturer. This discovery was particularly troubling because it suggested that some V-22 components might have been manufactured with substandard materials, a systemic problem that could affect the entire fleet. Following the Japan crash, the entire V-22 fleet was temporarily grounded while inspections were conducted. As of July 2025, according to congressional reports, 65 people have been killed in V-22 accidents, and component failures within the drive system have caused multiple crashes. These recent accidents have generated renewed scrutiny of the V-22 program. Critics argue that the aircraft remains inherently dangerous, with fundamental design flaws that make it more prone to catastrophic failures than conventional helicopters. Some family members of those killed have called for the Osprey to be retired entirely. Defenders of the program counter that when properly compared to similar mission profiles, the V-22's safety record is actually comparable to other military aircraft operating in demanding environments. They point out that since becoming operational, none of the crashes have been directly attributed to the tiltrotor design itself. So what's the truth about the V-22 Osprey? Is it a revolutionary success story or a dangerously flawed aircraft that continues claiming lives? The answer, like most complex questions, lies somewhere in between. The data shows that the Osprey's safety record has improved dramatically since the dark years of 2000. During developmental testing from 1991 to 2000, 30 people died in 4 crashes, a catastrophic accident rate that should have killed the program. Since becoming operational in 2007, the accident rate has decreased substantially, though 32 more fatalities and 12 crashes remains deeply concerning. When compared to other military aircraft flying similar missions in similar environments, the V-22's Class A mishap rate, the most serious category of accidents, has been higher than desired, but not dramatically out of line with other rotary wing and tiltrotor operations. Crucially, as far as investigators can determine, none of the operational crashes have been directly caused by the tiltrotor design itself. The accidents have resulted from pilot error, maintenance failures, and component defects, and other issues that can affect any military aircraft. The fundamental concept of tiltrotor technology has been validated. From an operational standpoint, the V-22 has delivered capabilities that simply didn't exist before. The ability to self-deploy across oceans, conduct missions at twice helicopter speed, and access locations beyond helicopter range has proven invaluable in combat operations, humanitarian missions, and special operations worldwide. The Marine Corps, Air Force Special Operations Command, and Navy have all committed to the V-22 for decades to come. New variants are in development, including the CM-V-22B for carrier onboard delivery missions. International operators, including Japan, have purchased Ospreys, demonstrating confidence in the platform. But the recent accidents, particularly the 2023 Japan crash, caused by defective components, demonstrate that vigilance cannot be relaxed. Every V-22 flight involves complex mechanical systems operating at the edge of engineering capabilities. Component quality, maintenance rigor, and operational discipline must remain absolutely uncompromising. The V-22 story isn't finished. The aircraft continues evolving. The improvements to gearbox monitoring, enhanced pilot training, and stricter component quality controls. The redemption story that began after the 2000 crashes remains a work in progress, requiring constant attention to prevent complacency from causing another disaster. From disaster to dominance, the V-22 Osprey redemption story is one of the most complex and controversial in aviation history. An aircraft that killed 30 people during development has gone on to accumulate over 600,000 operational flight hours, while delivering capabilities that have fundamentally changed military operations. The program survived crashes that should have killed it, overcame technical challenges that seemed insurmountable, and ultimately proved that tiltrotor technology could work. But success has come at tremendous cost. 65 lives lost, billions of dollars spent, and ongoing concerns about whether the aircraft will ever be as safe as conventional alternatives. The V-22's legacy will ultimately be determined not only by its past redemption, but its future safety record. If recent component failures can be addressed and accident rates continue declining, the Osprey may truly fulfill its revolutionary promise. But if accidents continue, the redemption story could become a cautionary tale about accepting unnecessary risk. If this deep dive into the V-22's complex story gave you a new perspective, hit that like button and subscribe to Project Aerospace for more balanced analysis of aviation's most controversial topics. What's your take on the Osprey? Let me know in the comments below. Until next time, remember, revolutionary technology requires revolutionary patience, uncompromising safety standards, and respect for those who have paid the ultimate price for progress. This is Project Aerospace.